determine that there is a solution, integer solution to the dependence equation, we are interested in knowing at which loop this dependence is at. If it's, say we have two loops and the dependence is at the inner loop and there is no dependence at the outer loop, then the outer loop can run in parallel. So what we want to do is to find the first loop which has a dependence. And how can we do that? Well, we subtract the solution vectors here, say j and I are the solution vectors, and then we subtract them, and that's the dependence distance. Distance in number of iterations for the different loop levels. So we can compare the index vectors and say that one is less than the other at a certain level. So for instance, this vector here is less than this vector at level 3. And if we take the union of all the relations where we compare the pairwise the indexes, then we get the lexicographic order, and the sequential execution follows the lexicographic order. Say we assume we find that I is less than j, then we subtract I from j. What does that mean? It means that the I corresponds to a certain iteration and j to another, and due to I is less than j, I obviously was executed before j. So we subtract one of the other, these two. When we do this, the compiler may subtract the wrong. So if we assume that I is less than j, and it instead subtracts j from I, and then the distance will be negative. What it should do then is simply to negate every element, and that is fine. Okay, so what we hope for is to get something called uniform dependence distances, and that is a dependence distance with only constants. And the reason for that is that then we can use something called unimodular transformations to change the loop iteration order. We do the same iterations but in a different order. And for that to work, we need to have uniform dependence distances. So if we conclude that there is a dependence distance with one unknown, then we cannot apply these techniques. We should also say, ideally, there are no dependencies, and then we can just run what we want in parallel, but usually there are dependencies. So if we have a loop nest with m loops, then we have m columns or m elements in each dependence distance vector. And when we analyze all pairs of references, that means pairs with the same array variable or matrix variable, then we are only interested in the set of dependence vectors, since they put each dependence distance vector, well, it's sometimes called distance vector or sometimes dependence vector, and or dependence distance. Each distance vector creates a limitation on the parallelization, and if we have multiple with the same contents, I mean identical, then they are not, we only keep one of them. So we have this as a set, and we store the set as a matrix. And what is more important is that even though we store this set as a matrix, it is a set, and therefore we can change the order of the rows as we wish, clearly, since there is no order. Okay, we distinguish between two kinds of dependencies. One is called loop independent dependence, and that means that the two index vectors are identical. So the distance is the zero vector. And with this distance, there is nothing that prevents concurrent execution of that loop. A loop carried dependence means that they are not identical. And the dependence is at a certain level, and that level is the first non-zero element of the distance vector.